This article is Image Processing with OpenMP. My name is Rick Leinecker. What we're going to cover in this article is faster image processing using OpenMP. We'll then analyze OpenMP's for construct so that you have a better idea of what's going on behind the scenes. After that, we'll take a look at efficient use of OpenMP's lock mechanism, which will help you avoid race conditions. Before we get started with the code, we need to say several words about 24-bit Bmp images. That's the type of image we're going to load into the example program, so we'll just take a look at it right now. First, the format is simple and uncompressed. It starts with the bitmap file header, which for this article we'll completely ignore. Next comes the bitmap information header, which contains things that we will use, such as the width and height of the image. And following that comes all of the RGB triples, each of which represent a single pixel. Now, you may want to extend this sample program, so let me say a couple of special notes about Bmp images. First, it's not really RGB triples, it's really BGR triples. For whatever reason, the red and the blue are swapped. The second thing is that Bmp images are actually stored upside down. So you start actually at the last scan line and work your way to the first scan line. Okay, so let's take a look at some source code. The first thing I'd like to point out is this load original image function. It simply loads this opens sample image.bmp, which is included in the sample demo project, which is zipped up and can be accessed from this web page. It gets the file length, it allocates the buffer, it reads in the entire file, and then just to point that out, that there's a bitmap file header, a bitmap information header, and then following that is the actual RGB data. So I've got pointers to all three of those things. Okay, so in order to create a benchmark timing, I created a negative image using normal serial techniques. So here is this function that does just that. Goes through and just does some sanity checks. Here it creates the new negative image buffer and its three associated pointers, copies in the original data. Here I get a time just so I can have the benchmark time. And it just goes through and flips all the bits by XORing with FF or 255. I get this ending time, and then I figure out what the elapsed time is. This way I can compare it to the parallel version. Okay, next comes creating the negative image using parallel processing through OpenMP. So here are just some sanity checks. Here I create the new buffer and point the header and RGB data pointers to that, the appropriate place within there. Copy the original data, do a couple of pre-calculations. Here again, I'm going to get the start time. This is the big difference. This directive, OMP parallel 4, is going to tell OpenMP that I want this block to be done with parallel threads. What it'll do is figure out how many threads I've got available, and that could depend on how many processors you have and what the system is currently doing, but it will give you a team of threads that will perform this block right here. Finally, I go ahead and get the ending time and calculate the elapsed time. Now, I'd like to point out this is actually a simplified directive, but I'd like to point out what it's doing in a more verbose way, and I've got some code below here. So the first thing is, I need to tell you that this will execute as many times, this printf will execute as many times as threads you are given. For instance, if you get 4 threads, then that will execute 4 times. Okay, so that's an important point to note. Now, we're going to do this a little bit differently, where instead of the OMP parallel 4 directive, we're just going to say OMP parallel. This tells us how many threads we got, and by the way, this also will execute once for every single thread that we're given. So here, we find out the number of threads we were given. We find out the thread number of the current thread that is executing. Okay, so let's say we have 4 threads. The thread number will either be 0, 1, 2, or 3. And then we do the same loop, except we start at a different number. Before we started at 0. But here we start at either 0, or we start at 1, or we start at 2, or we start at 3. And we simply increment by the number of threads. And here for this example, we're assuming that we've been given 4 threads, although it really could be pretty much anything. So that's the breakdown on how the simplified syntax actually happens. Okay. So let me go ahead and run this now and just kind of show you what the program is going to look like. And you'll notice that you have the original image and then the negative image. And this window is kind of off the recording area here, but I'll scoot it on over and you can see that we got a 28% advantage in performance here by using the parallel processing. Okay. The last topic I'd like to cover is how to prevent race conditions. Now, a race condition will occur when multiple threads are trying to access the same shared memory location. So let's say there's an array and both threads, or 2 threads, are trying to access element 12. One may be adding 17, the other may be adding 14. Now, which of these is going to win? Well, the answer is you don't know. It just depends on the exact precise timing. So there needs to be a way to arbitrate between multiple threads which are trying to access the same location in shared memory. Now, the article talks about two main ways. One is using the critical pragma, and the other is using the atomic pragma. And those are really good, and they work well. The problem is, if you use them in certain situations, such as we're going to show you, then every single thread has to stop and wait every single time. And what you end up with is, for all practical purposes, just simple serial code. So what we're doing in this article is to sort of show you a better way for certain situations, not every situation. So let's start off with saying that we're going to create a histogram of the hue values of the entire image. Now, hue values range from 0 to 359. So we're going to create 360 locks that will only lock on those actual values, the hue values. So here I've got this method, create locks, and I create 360 locks. Now let me scroll down to where I create the histogram. Sanity check for the memory, some pre-calculations. Now here, what we're doing is we're looping through all of the pixels. Okay, we're converting the RGB values to HSV, hue saturation value, in other words. Now here, we're setting a lock. And the lock is only going to be for that particular hue value. So it's not the same as using a critical or atomic pragma, where all threads have to wait. The only way another thread will have to wait for this is if its hue value that it's trying to alter is the same. So then I wait, maybe, suppose I have 254 as my hue value. So it waits to make sure I can alter that particular memory location. I alter the memory location, and then I unset the lock. But the chances of another adjacent pixel having the same hue value, or even multiple adjacent pixels, unless you have some sort of a solid image, are very low. So this gives you a good way to prevent race conditions without significantly affecting your performance.